Good morning. Today's bell ringer. We're looking at how do computers speak to each other? Do they use a language, and what language is it? A lot of people probably pondered this, those that didn't come into the know back when they started creating computers. There is a language they use. It's called machine language. And that machine language uses a series of ones and zeros that the computer can read. The reason the computer is able to read them is because all computers know are electrical currents. And if the electrical current is on, that's a 1. And if the electrical current is off, that's a 0. And that's how they actually communicate. Now, that's a really simplified version because they do this billions of times a second. And so they're able to do what we do about the same frame speed, sometimes faster. So lots of times faster when it comes to calculations. But anyway, that's how computers speak to each other. So let's talk about good things. Anybody have any good things? Yesterday was October 2nd. I had a couple people that are gaining ground on trying to be Brazos Valley Player of the Month. Not sure exactly who they are, not only in football, but also in volleyball. You guys might know who they are. Don't know the outcome of that from yesterday, but you know, it is what it is. If they're not the Brazos Valley Player of the Month, they're definitely the Rudders Players of the Month. So keep that in mind. All right, so today's lesson, it's in a chapter of a short book that I created myself a couple years back called TCP IP. And what it is just TCP IP is IP is the only thing you really need to consider yourself having to understand. It stands for Internet Protocol. And we're going to talk about binary to decimal translation. We'll also talk about why it's important for computers or for us to know how this works for the future. Just a couple images here looking at how we actually translate from binary to decimal. It's really simple. Each time we look at the number line in a decimal configuration, we can see it. We're looking at, this is on this side, this is decimal, how to decimal to binary, how to binary to decimal. This is some good graphics to show you how to do things. So what it is binary numbering is a base 2 numbering system. I'll explain that a little bit further in a second. Our decimal system is a base 10. All of our numbers are based on the digits 0 through 9. So anyway, IP addresses or network addresses are common to everyday internet users. We've probably seen them. If you look over to the right, you'll see one. These details are essential for information to be accurately and securely passed from one computer to another. Knowing what they mean, in other words, which numbers are valid, and how they are calculated is extremely important. So do you know what these numbers 216.132 but 98.198/24 means? Probably not. Doesn't take much of a scholar, though, to know what it means. So how do computers communicate? Consider the light switch at the door. What is its job? It simply allows the circuit to either continue or not continue, which allows the light to turn on or stay off. On is 1 and off is 0. That basic principle is the backbone to computer communication. Binary numbers only have 2 digits, 1 and 0. A binary octet has 8 binary digits. So we have 4 binary octets here. And if you go back one page, you can see this number 216.132.98 and 198. Right here, that's a series of 4 octets or 32 bits. Or a bit, actually. So 11111100 is the decimal equivalent to the value each binary number gives in the octet is 252. This decimal equivalent is 255, all ones. This is the decimal equivalent of 10, and this is the decimal equivalent of 42. We'll explain how that works here. So when we convert decimal 35 to its binary equivalent, we need to think about it this way. The base is the exponent, okay? The base is 2. The exponent is the number. Notice that we have them listed in sequence from 0 to 7 all the way up here. There's 8 digits. So we're going to look at it this way. This is the place value in binary numbering. So in decimal numbering, the first place value is the zeros. The second is the tens, then the hundreds, then the thousands, 10,000s, 100,000s, millions, and so on, right? Well, they have a place value in binary numbering too. The place value for the first digit is what we call the ones digit, okay? All right? And then we have the twos digit, the fours digit, the eights digit, the 16s digit, the 32, the 64, and 128. Now, so you understand how this works, we can derive every decimal number by adding all of these numbers together. But there's only one number in this whole system that determines whether or not the number is odd or even. And I want you to think about that for a minute. We'll look at it in a second. I'll explain that answer to you here in a minute. So the binary equivalent to the decimal number 35 is 001 00011. All right? So binary decimal translation. If we're using 8 binary digits to represent each decimal number because IP addresses are represented by 4 octets or bytes, which means 8 binary digits, bits, to each octet for 32 total bits. 4 8 binary numbers, which is 32-digit binary number. Oops, went too far. Each binary digit or bit is much like a decimal digit. Instead of using a base 10 for each digit, binary uses a base of 2. This is useful for computers because they simply use a series of on-off switches to count, make letters, form commands, etc. All right, 23,255,781 means, and I wrote it out, 23,255,781. We know from elementary math that each of the 8 digits in the number correspond to a number sequence that has a specific purpose in its understanding. That's digits value and subsequently the number's value. So let's break it down. This 7th digit, the 2, is in tens of millions, or 2 times 10 to the 7th, which is 20 million. The 6th digit is 3, and that's in millions. It's 3 times 10 to the 6, or 3 times a million, which is 3 million. 5th digit, 200,000, 10 to the 5th times 2 is 200,000. 5 is in tens of thousands. 5 times 10 to the 4th. Notice that the same number that's in the exponent is the same number of zeros that follow it. 5 times 10,000, 50,000. 5 is in the thousands, 10 to the 3rd. 5 times 1,000, 5,000. 7 is in hundreds, 10 to the 2nd, 700. 8 is in the tens, 10 to the 1st. Notice there's no number up there. You don't have to because it's represented by just the number itself. 8 times 10 is 80. And then ones is 1 times 10 to the 0. Now, recall the law of exponents. Anytime you raise a number or any sum, any number value, any value up to 0, the resulting answer is always 1. So 1 times 1 is 1. And some of these numbers, when you add them up, is 23,255,781. So we don't actually do this to determine the value of the decimal number because we've all learned the decimal system to describe the value. However, we do use the same exact process as above in binary mathematics, except that we use 2 as our base instead of 10 when writing the number. This chart is not very different from one that describes decimal numbers. It's just another way to look at numbers. Since computers use on-off as their way to communicate, a number system using 2 as the base instead of 10 was created. Each digit is multiplied by 2 raised to the power of its sequence n in the number, and the sum of those calculations is the decimal value of that binary number. Now, I want you to think about this. You ever wondered why we use the number 10 as our numbering system? Look at your hands. How many digits do you have? Is it strange that we use the word digit to describe a number too? Yeah, that's not an accident. That's not just totally coincidental. That's on purpose. Since humans for like ever have had 10 fingers and 10 toes, they've used it to count, and that's how they've done it. If we were just a being that had just 2 arms, we would probably use the binary numbering system because it would be familiar to us. We tend to use, or people, animals, whatever, tend to use what is familiar to them to help them along. All right, We couldn't create the same number as 23,255,781 with only 8 binary bits or a byte, but we could create numbers from 0 to 255. Let me show you what that means. For example, you use 11010011 and using the chart, look at what binary position each one is in, then turn that number on and add it to the sum of the digits. Now, we simply add all the calculated decimal values together to find the decimal equivalent. So let's look. We've got a 1 here down at the bottom. We're going to turn the multiplication on. So 1 in the first one is 1 to the 7th, or it's 128. 1 times 2 to the 6th, 64. 0 times 2 to the 5th, that's 0. 1 times 2 to the 4th is 16. 0, 0, 1, 1. So we have a 128, a 64, a 16, and a 2 and a 1. And that's what we added together here. We ended up with a 211 as our answer. All right. So what is the decimal equivalent of each of the following numbers? Can you use the chart to translate a binary number in a decimal every time? Providing the number is only in 8 binary digits or a bit, we'll always find the decimal equivalent to fall between 0 and 255. So look at the first one. We've got 128, 64, 32, and then 8. Wonder what that comes out to. 232. We've got 128, 8, 4, and 1. That should be, I don't know. Is it odd or even? It's odd. Look at that. The next number, we only have 2 digits, and they're placed right at 32 and 16. So we simply add those two number together, and we should get 48. And we do. Now, check it out. There's only one number in there, and it's nestled right there in the 16. So that should be the 16 should be our answer, and it is. Now, we have an 8 and a 4. What's 8 and 4 together? When we add those together, we get 12. Let's see if that's what we get. It is. And the last one has 3. Has 4, 2, and 1. That is 7, of course. Now, I'm going to launch you with this. I may take a little time in class to explain how the numbering system works. Just recall that when you're adding up numbers from 0 to 10, after you get to the last single-digit number, you add 1 to the second digit of a second-digit number and turn the last digit into 0. We do the same thing in binary. Okay, so I'm going to launch you with this quote from Buddha. Unity can only be manifested by the binary. Unity itself and the idea of unity are already two. Okay, that's kind of complicated and may have some religious overtones. I'm just quoting the guy. I'm not Buddhist, not by any stretch of the mean, but I thought it was really cool that even in their search to become one with reality or one with whatever, they determine that there's not just one, there's always binary. So that's pretty fascinating. Anyway, there's an assignment in the Google Classroom. Please watch these videos before you try to take the assignment because you're going to have to redo them if you don't have any experience doing these already. So anyway, thanks for watching the video again, and be blessed, be a blessing. Don't forget to do the assignment in the Google Classroom. Have a great day, folks.